what I wanted to talk about today is the sort of distillation of, I guess, some work that I've been doing, and I acknowledge my colleague Graham Begg as a co-author, but it's work that's been informed by very, very many people over a long period of time, and that's putting gold and I guess a copper deposits, certainly the sort of copper deposits that occur in convergent margins, into an overall framework that we can actually use for predictive targeting. And my main interest in understanding geodynamics and architecture is very much around how can we use it for predictive targeting, remembering that to do things practically in this business, it's really about distilling out what are the absolute key patterns that have got a spatial context to them, because if they don't have a spatial context, they really don't help us with prediction. So what I want to share with you today is a model for practical predictive targeting in convergent margins. So I'm really talking about the whole range of gold, copper, and there are some other commodities as well, like zinc, skarns, and so on in there, but primarily gold and copper. Convergent margin settings host pretty much all the world's gold, and I'm including, by the way, orogenic gold deposits in this context, and they host a very large amount of the world's copper deposits, basically all the porphyry style deposits, not the sedimentary basin hosted deposits. So a very metallurgically significant environment. So and I guess, look, before I go on, some acknowledgements, builds on the great work of many others, and my inspiration and mentoring goes back to David Groves, who I think was light years ahead of everyone else in this space. But I particularly like to acknowledge Bob Laux, whose seminal work, which really started with an industry-based study a couple of decades ago. So it took quite a while to sort of really percolate out into academia, but I think was a fundamental key to start to unlock this sort of process-based understanding of convergent margin metallurgy. So I'm going to start off with some sort of philosophical comments. And the first one is that the philosophy that guides me when I think about ore deposits, and I think about ore deposits, particularly in the context of regional targeting, is, and this is something that I've come to from 40 years of sort of empirical experience doing this, is that ore formation is the predictable, a very important word, consequence of certain particular, meaning that we can define them, although relatively rare, segments of the four-dimensional evolution of host terrains. So what I'm saying there is that we have a host environment. In this instance, I'm most interested in the convergent margin suprasubduction type environment. If those environments evolve through a range of geodynamic scenarios, you can think of it as sort of a parameter space, a four-dimensional parameter space. And what I'm saying, at certain points in that parameter space, we do make ore, and we can also identify the parameters that will make generally bigger deposits rather than smaller deposits. And this stands in contrast to what might be an alternative view, and there's been several publications over the years where greats in our science have been asked to talk about what makes a giant ore deposit, and they basically all come up with, well, it's a coincidence of a number of various factors, which in a way is similar, but in a way isn't, because that's saying, well, it's some random stochastic coincidence. And if that was the case, we wouldn't see the clustering and the patterns that we do see in deposits. And of course, it would mean that they're inherently unpredictable. Okay, so the basic hypothesis that I want to share with you today and provide in this short time I have available, so I want to try and articulate this hypothesis, provide a little bit of support for it, and show you how you might apply it. It is an oversimplification, like all things. I think any model, qualitative or even quantitative, is always a major oversimplification of nature. The question is it a useful oversimplification? And I think that probably is the case. So this hypothesis says that to a first order, we can explain the regional context. So these are concepts that are relevant for targeting at the regional scale of all convergent margin related copper and gold deposits by the interplay of only two fundamental processes that operate within a range of geodynamic contexts. And the idea is that then ore formation requires these periods of anomalous geodynamics, which are transient in both time and space. And that leads us to this concept of dynamic fertility. And we often talk about fertility, but in this particular framework I'm sharing with you today, perhaps it's a new concept, but we need to separate out the ideas of dynamic fertility and static fertility. And I'll sort of elaborate both of those. And then the implication of this hypothesis is that the fundamental unit of regional scale targeting becomes something that we call fertile geodynamic anomalies. So these are domains that they have a spatial context, but they're also restricted in time as well, that represent the context in which fertile ore forming mineralization processes occur. And then the last point, which is I guess what it's all about, is that these fertile geodynamic anomalies are predictable if we understand the geodynamic history, which is what I'm going to focus on here. But of course, geodynamic history always is superimposed on fundamental lithospheric architecture, which for the purposes of this talk, I'm going to take as a given that we need to understand that context. So in summary, I believe this is a simple, well, I think a relatively simple, but powerful and practical concept. So what are the two fundamental processes that I'm talking about? The first one I refer to as the Loucks process, because it really was first articulated by Bob Loucks. Others had identified an empirical relationship between crustal thickening and porphyry ore formation, but Bob was the one who really identified what that process probably was. And that is this idea of prolonged high pressure replenishment, fractional crystallization of hydrous arc magmas deep, so probably at the base of the crust, to produce extremely hydrous magmas, which exalt volatiles at anomalously high pressures. And that's really the key thing about the Loucks process, is that we have magmatic volatile exsolution at really high pressures, which results in very efficient partitioning of chlorine and therefore copper and sulfur into these fluids. And this turns out to be the process that's a dominant process for copper ore formation. So, you know, if we see a copper-only porphyry, we're probably looking at just the Loucks process. The other key process is one that I've coined the term fume process for fertile upper mantle extraction. And the idea of this is the selective extraction of a gold and volatile rich magma from a metasomatized upper mantle source region. And that metasomatism is probably a product of earlier sort of subduction zone processes. And the extraction, the material that's extracted, typically in the form of an alkalic magma, but of course on the way up to the surface, that magma can devolatilize, those fluids can interact and hybridize with other fluids and so on. And this is what I would argue is the dominant process for gold ore formation. Now, one of the ways to think about each of those two processes is to say that, well, convergent margins are important because they're fundamentally a site of water being recycled into the deep earth and back again. And if we think about then the two environments where we can access water-rich magmas, one is directly off the slab, which is really what the Loucks process is about. The other is from a domain in the lithosphere where we've stored large volumes of water, and that's what the fume process is about. So it's all about water. And the key point is both of these processes require anomalous geodynamics within the overall evolution of a convergent margin. So this slide just quickly shows a couple of papers where these concepts were first articulated, or maybe in the case of Bob's work, it was really first presented in unpublished company work many years ago, back in 2000, I think, but we subsequently entered the public literature in 2014. But I think there's a more, I think what I'm showing you there is a 2011 paper, which is, 2021 paper, beg your pardon, which is a more coherent summary, but Bob did publish stuff in 2014 as well. Where's my... Okay, so just to summarize, I'll try and get this out of the way here. One of the ways of looking at these two processes, and this is a diagram that my colleague Graham Begg produced some years ago, is to look at porphyry copper deposits, the Laux process operating, ordinary arc melts, trapped at the base of the crust, fractionating to produce these very volatile rich magmas, whereas the fume process is a lot more about concentrating volatile rich fractions in the upper mantle, extracting those to make a gold deposit with a potential range of different crustal hybridization and fractionation processes going on. The geodynamics of the Laux process, I don't want to spend too much on this context. I think this is sort of well known to most people now who think about these things, but the basic idea is that, a typical normal, stratovolcano system in an arc, if the arc-derived magmas, end up fluxing through to the surface pretty effectively. But if we clamp these systems with compressive stress, which happens primarily during related to orogenic events, and there's a couple of different ways we can make that, including obviously collisions, but also when slabs shift to a flattening orientation, what that does is that reduces the flux to the surface, reduces volcanism, keeps things deep, and allows them to fractionate. And if we're continuing to bring in magmas from the mantle, Bob's idea is that over time, these various cycles end up producing a very fluid-rich magma. And there's a lot of support for this in a whole range of different dimensions. So that's just the process of where over time, with multiple cycles in this sort of envisaging this deep moho level magma chamber, we build up things like the water content and probably critically the chlorine content in the melt. Okay, so what about the fume process? Well, the idea of the fume process is that gold deposits form when gold is preferentially mobilized from an upper mantle source into the upper crust. And this occurs because partial melting of the mantle source concentrates gold in a volatile rich melt fraction. Although, there is a little bit of work coming out of China now that suggests, well, maybe these volatile rich melt fractions are not particularly enriched in gold, but the key thing is that they're enriched in these volatiles, which then partition, particularly sulfide related volatiles partition, and in a way that then extracts the gold effectively into the magma. And I think into the melt, into the coeval fluid. And I think there's a lot of work to be done on that. The key point is that selective melting of the mantle source is essential to make this process work. And that, as I'll elaborate shortly, is the key link to geodynamic context. Prior metasomatism and volatile enrichment of the upper mantle source is required because to provide this sort of volatile rich, and these things are probably the volatile rich fraction probably forming as veins in the upper mantle that can be easily melted. And the most effective mechanism for this selective melting is some sort of minor extension, although it might be that the percolation of a low degree partial melt from below, for example, associated with initial plume impact, like we see with the initial plume impact of the Yellowstone hotspot associated with bonanza gold deposits in the Miocene of Nevada, might also work. And the key point, though, is that in all cases, selective melting will require an anomalous geodynamic environment. So what's the evidence for this process? Well, we see an ubiquitous association between alkalic magmatism and gold mineralization across a very wide range of geological settings. We see good evidence that Many alkalic magmas are in fact enriched in gold. I mean, the late Nick Rock was speaking about this over 35 years ago. And really, alkalic intrusions pretty much are the only major rock type that are systematically enriched in gold. And then for me, you know, as someone who applies this stuff in my day job, it's really seeing the geodynamic context of gold mineralization in these anomalous settings which favor strike-slip faulting and or incipient extension. We see these themes again and again, and these are effective mechanisms for mobilizing the upper mantle source. And then, I see all those same processes being totally relevant to orogenic gold deposits. Many of you will be aware that historically there was an orthodoxy around orogenic gold deposits that invoked crustal metamorphism. I think there's, in more recent years, there's been very, very compelling evidence that those models are not viable. I refer you to some really well-written and well-summarized syntheses by David Groves and co-authors, heavily based on a lot of critical new data coming out of China. I don't really want to go into this conversation now, but I do think that the evidence is quite strong. So one of the things we see in the upper mantle is that most of the upper continental mantle probably, and this is the work that's come out of my colleague Graham Begg and Macquarie University over the last several decades, is most of the continental mantle probably forms very early, probably by the Mesoarchean, and initially it's very depleted. So it has a composition that's dominated by things like dunite and harzburgite. And but what happens over time is it gets progressively reworked, metasomatized, enriched. And if we compare the typical depleted mantle here, and look, this is the work of Saunders et al. From a few years ago, and look at the distribution of gold in that, and you can see it's heterogeneous. You know, there's obviously little veinlets in there. You occasionally get the higher samples, but then if you look at pyroxenite xenoliths, which are probably representing sort of frozen mafic melts metasomatizing the upper mantle, you can see straight away that refertilization is increasing that gold content. Some work from the Yilgarn craton of WA from Choi, showing that, you know, there's a number of different periods of extraction of various alkalic magmas, and what they tend to do is be enriched in a tendency to spread to a relatively high gold numbers, significantly above the sort of, you know, the background levels. We often see a relationship in many provinces with gold mineralization being associated with late mantle-derived magmatic rocks. Here's a 2007 summary for the Superior Craton from Beak House. And more recently, you know, we actually have some nice studies which have actually shown this process of gold mobility in the mantle more or less caught in the act. So this is the work of Tessara et al., who were looking under xenoliths that were sourced from underneath the Desierto Massif, which is a gold-bearing province in Argentina. And they were finding these sort of veinlets that were quite enriched in gold, you know, to the point they had discrete gold particles in it. I guess the question I have when I see something like this, okay, it's unequivocal evidence for a gold-enriched vein network in the upper mantle. Are these veins the actual fume source sitting there waiting to be extracted by an event, or is this actually the fume process? You know, it is the fume product which has actually been trapped and frozen in these particular samples. And I think these are things that we don't understand yet. Just a bit of a comment on alkalic magmas, and we've said how there's a strong relationship between those and gold. It's just important, and maybe this is a bit basic, but to kind of remind ourselves, what do we mean when we describe a rock as alkalic? That is a rock that has significantly higher contents of the alkali elements, potassium and sodium, at any given fractionation state than typical background rocks. Now, of the 10 most common rock forming elements, there's only 2 of them that are actually incompatible during melting, and that's potassium and sodium. So basically, in any melting process that concentrates incompatible elements, we'll concentrate potassium and sodium, and therefore, these things will be alkalic. And the 2 main ways to do that is sort of low degree partial melting of some bulk mantle source. It could be a sort of rising plume. So for example, the first layer of volcanics that come out of the Hawaiian plumes are alkalic. But alternatively, we will also get to the same place if we just selectively melt some volatile, and because volatile elements are obviously incompatible elements, a volatile rich, incompatible element rich fraction of the mantle. So there are some interesting things though about this alkalic aspect of these rocks, because the CO2 solubility of mafic melts depends quite strongly on the presence of the cations, calcium, potassium, and sodium. These alkalic rocks have much higher CO2 content than background thyolitic magmas. And why that's important is, I think that my gut feeling is this is a big part of how orogenic gold deposits fit into the unified model, because if they're forming from the fume process that's overprinting more of a sort of a retro arc context, it's reasonable to suppose that we may have more CO2 in the mantle. If we've got more CO2, what's going to happen is that, the other thing that CO2 does in the magma is suppress the partition of chlorine into coexisting magma fluids. So more CO2 is going to give us a fluid that A, will be lower salinity. It'll still have sulfur, so it'll still be able to complex things like gold in a bisulfide complex, but it will have a lot less base metals. But it will also, because it's full of CO2, it will devolatilize. So any sort of magma fraction will lose its CO2 or tend to lose its CO2 a lot deeper, and therefore, or tend to lose its fluids a lot deeper. So therefore, it's more likely that these things will give us fluids that might end up looking a bit like metamorphic fluids. It also why these fluids will unmix, if we believe unmixing is a fundamental ore depositional process to make ore phase separate, and that'll happen at a significantly deeper paleo depth than we see in less CO2 bearing systems. So this is a slide is just making that point that the relationship, as we increase the CO2 in the fluid, more chlorine stays in the melt and less goes into the fluid. So this basic dichotomy we see between chlorine rich base metal fluids and low salinity gold rich fluids, I think can easily be explained by the role of CO2 affecting melt fluid partitioning. Okay, so one of the key observations that's really relevant when we think about convergent margins, or key questions, if you like, but it also really does pertain to the model, is how do gold and copper mineralization relate? And we've talked about 2 separate end member processes, the fume process driving gold and the Laux process driving copper, but they commonly coincide because the same geodynamic conditions may favor both processes operating at the same place and time. So this is a sort of fairly old compilation from Bob Laux's work, but I think it's still a pretty profound pattern where Bob is showing us that on this axis, we've got a ratio which basically can be interpreted as the proportion of sort of metasomatized mantle contribution relative to deep crustal fractionation, and on this axis, the degree of fractionation. And we can see very clearly that the parental deposits the parental intrusions to gold sit up in this corner. So less fractionated, more mafic, with a stronger sort of mantle metasomatism signature, whereas the copper only deposits tend to be here. So less of a sort of metasomatized mantle signature, but a stronger fractionation signature. So consistent with, the end member Laux process, where an arc magma is just fractionating at the base of the crust. And just to take you back to these two perspectives, the Laux process and the fume process perspective that I shared with you before. Sorry, this is the same process now, but just highlighting increased enriched mantle contribution relative to crustal fractionation, and here is increasing crustal fractionation. We also interestingly see this difference in the geodynamics of ore emplacement as well. And this is some interesting work that Massimo Ciradia published a little while ago. And this diagram is showing something that we probably already know, and that is that if we look at the amount of gold, and these are for a whole a large population of porphyry deposits, porphyry copper gold style deposits. But if we look at the ones that are dominantly copper, they're dominantly calc alkaline, whereas if we look at the ones that are dominantly gold bearing, they're high K calc alkaline or alkaline. So what our model would predict. So the interesting thing though is that if we do something else, and what Ciradia has done here is looked at gold content in terms of the duration of these multi-stage porphyry events, we see quite a clear difference where the classic sort of calc alkaline copper deposits seem to be emplaced over a significantly longer duration, and this is really the duration of sort of multiple intrusive pulses within a broad porphyry camp, whereas the gold deposits seem to be emplaced much more rapidly. I mean, longer times generally produce bigger deposits, but there's two very different curves there. And I think this is very consistent with these different geodynamic models. I mean, the Laux process is about progressive fractionation in this deep crustal magma chamber. The fume process is about tapping an existing source region. So I thought that was really interesting when I saw that data. So given the framework that we presented above, we can now start to identify the predictive geodynamic patterns which control fertility. But before we do that, we need to sort of introduce a bit of a conceptual framework. So the first point is that we need to think in terms of two types of regional fertility: static fertility and dynamic fertility. So in this context, static fertility is the requirement for some sort of metasomatized upper mantle source region. And this is an inherited property. It's not dependent on syn mineralization geodynamics. It's something that exists prior to the syn mineralization event. And this, in our framework, will only be relevant to the fume process and gold metallurgy. Dynamic fertility, on the other hand, is the requirement for a favorable anomalous geodynamic context that allows either or the fume, or both, the fume and Laux process to operate. And these dynamic contexts will be transient in both time and space, and they'll be driven by heterogeneities in regional scale geodynamics. So I should probably add that heterogeneities in regional scale geodynamics are often in turn driven by heterogeneities in regional scale architecture, the Bolivian orocline being a very, very good example. And these dynamic fertility is relevant to both copper and gold metallurgy. So static fertility, a few things we can say is, in general, the fertile upper mantle source seems to be quite widespread and widely available relative to the scale of gold provinces, but there's still some important variability. It looks like if we've just got the original Harzburgite lithosphere, we don't make gold. And I'll show you a neat example in a minute from the Archean slave province. Based on the work of Wang et al., it kind of looks like once the old metasomatized lithosphere is gone, this is in the North China situation, the magmas coming out are no longer gold rich. Where the old lithosphere was there, they were gold rich. Afterwards, they're not. But most importantly, and I think probably the thing that's sort of I'm finding is most useful in my regional targeting, is areas of significant rifting and juvenile input immediately prior to the gold event, but far enough before the gold event that they can't actually be implicated in the event tend to be most fertile. This is really clear in things like the Yilgarn and Abitibi, where we see the Norseman lunar belt and I guess the Mount Magnet Meekatharra belt. These areas where we've had the strongest juvenile input, and the proxy of that is just the sort of the youngest mantle derived greenstones, particularly things like komatiites, the southern volcanic zone of the Abitibi. So I don't exactly know why that might be, but the most logical interpretation is that these are areas that still have a relatively elevated lithosphere geotherm, so that they're, when they're hit by the geodynamics that favors the fume process, they do a much better job of extracting out the stuff that we want to see. So here's the slave, and it's showing that the various supercrustals in the slave. The mauve ones are flysch dominated sequences, and the green ones are basalt dominated. But the key point is that there's some big gold deposits in the slave, and obviously there's some well-known diamond deposits, but there's a pretty strong sort of antithetic relationship. I mean, almost no gold deposits in the central slave kimberlite province, despite significant presence of sort of Neo-Archean flysch. If we look at the Yilgarn, and we look at samarium neodymium mapping of granite, which is really a proxy for the mixing of a juvenile component into the lower Yilgarn crust, we can see quite clearly an association between the areas with the greatest juvenile input, so the Norseman lunar belt here, and within the sort of this older you-and-me craton, quite a strong association of gold with the bit that actually gets the most significant juvenile input. So this corridor here, this sort of Q Meekatharra corridor, pretty much the only place we see 2.7 GA komatiites. They're not nickeliferous, but it's pretty much the only 2.7 GA komatiites that we actually see in the you-and-me craton. And I've actually seen this pattern in Cenozoic environments as well, where precursor Jurassic rift zones, when they're overprinted by a Cretaceous event, seem to, in places like northeastern Russia, seem to have the strongest gold endowment. Okay, so dynamic fertility. So within the evolution of our host origins, this is the most important time, but not most of the time. And if we think about the Laux process, the dynamic fertility that we're interested in is fundamentally the requirement for some anomalous compressional geodynamics to be superimposed on arc magmatism. And this is typically a proximal collision, but it also can be some response to larger scale geodynamic forces. And this is what we see along the Andean margin, where a whole margin goes a lot more collisional, and that's generally associated with flat slabs as well. Flat slabs often being perhaps more of a response rather than a cause of some of this stuff. If we look at the Tampakan example, so this is a relatively young, almost Pliocene example of mineralization. This is from Laux and Ballard's work, and it was really the study of Tampakan that really launched Bob on this pathway. But he was basically able to show that, you've got the one stratovolcano complex that you've got volcanoes which record a sort of 7 or 8 million year history to the present, and inferences from this work showed that back in the late Miocene, the Moho was probably only at 21 kilometers, but then subsequently there was a crustal thickening that went on, and that crustal thickening was associated with the period of mineralization. But what's sort of really neat here, and see if I can move that, is the work that sort of Bruce Rawlack did here, which was that if you consider that the Tampakan deposit is forming in sort of Mindanao, and which is a fairly complex zone between the Sunda Block and the Philippine Sea plate, and there's quite a few sort of microplates and subduction zones and so on. But because you sort of know what the overall convergence rate is, and because you can sort of rationalize or explain a lot of that convergence by looking at the seafloor striping and so on, you can make an assumption that the bits that can't be accommodated by slab subduction in that overall convergence are accommodated by orogenic shortening. And what basically happens is that there is a collision, a microcontinental collision, which drives orogenic shortening, and this is why slabs do reverse. Then you have a switch to subduction reversal, because basically the stress has to be accommodated somewhere else. So what we see is that the Tampakan forms at exactly that peak of orogenic shortening, exactly as predicted by the Laux model. Just an interesting historical aside, many years ago, Mike Solomon made the observation that there was an association between zones of subduction reverse or double subduction in the Southwest Pacific and porphyry endowment, and which was an interesting observation, but clearly that in itself was not, could not be a generic observation, because when you go to the Andean margin, you've had subduction going the same way for hundreds of millions of years and lots of big porphyries there. But what the common factor that they were both saying was orogenic shortening. They're both telling you orogenic shortening. It's just when you're in a Southwest Pacific environment with lots of microcontinents, if you have a pulse of shortening, it will generally be, the response to that will generally be subduction flipping to the other side, where of course that can't really occur under a big continent like South America. So if we talk about dynamic fertility in the context of the fume process, that requires three fundamental dynamic conditions. First of all, we need a continuous pathway from the upper mantle to the upper crust. We need selective extraction of a gold-rich melt fraction from the upper mantle source region without significant dilution. So we want incipient extension only, and we want minimum dilution of the ascending gold-rich melt by bulk crust or slab-derived magmatism. So if we've got the whole lower crust melting, for example, it's probably not going to be, or it isn't going to be, a good environment for the fume process. And these things, as always, can occur at multiple nested length scales. Just some examples: the collapse of the laramide origin, laramide, which is assigned to a flat slab in Southwest US, and that extension just basically progressively then shifts to the Southwest. That's associated with the Great Carlin Trend deposits, associated with Bingham Canyon, which is a gold-rich deposit. And basically, we can demonstrate in detail that as that origin unzips, when that unzipping hits these fertile mantle-derived areas, that's where we get these big gold deposits. The other thing that understanding the fume process and understanding geodynamics does is it helps us explain some patterns otherwise I think are pretty enigmatic. So it's been long recognized that when we look at orogenic gold, we have a correlation between the peaks of orogenic gold and the final stages of supercontinent assembly, and including things like the assembly of Gondwanaland in the Pan-African. And I think the reason for this now starts to become very clear, and that is it's the final stages of shortening where we actually get the most strike slip tectonics, which is a very favorable environment for the fume process via incipient extension. And I think we're all probably familiar with these ideas that a terminal orogenic collision can often be accommodated in lots of sort of strike slip. And in fact, it's at terminal stages of continental collision that we often maximize strike slip. And it's sort of counterintuitive, but what we're really saying is the terminal stages of continental collision actually maximize our opportunities for incipient focused extension of the type we need for the fume process. And a really good example of that, of course, is Murrintau and the Tian Shan gold belt, which we know form at exactly the peak of Pangaea, the formation of the Pangaea supercontinent. So here's some of Sasha Yabachuk's work showing that we have this long-lived accretionary margin on the edge of Laurasia, but when we bring in these fragments from Gondwana as part of Pangaea assembly and have this terminal collision, it's this strike slip deformation that's been driven at that time where we see the peak of gold. We also see quite a similar thing in the Andes, where the Andes has a strong history of metallogeny from the mid to late Cretaceous, and I think that's part of the geodynamics of the Atlantic Ocean opening and sort of making that South American margin relatively compressional. But it becomes a lot more compressional at the beginning of the Miocene, and that's partly reflected in the Nazca plate convergence vectors, the Petrocasus work. But you can, where we switch to orthogonal convergence, that's when the altiplano and all these things come up. But what's also interesting is that pretty much all the gold, or at least the gold since the Mesozoic in the Andes, forms in this Neogene time. These earlier events before the Neogene in the Cretaceous, they're very well endowed for things like copper, but they're relatively poorly endowed in gold. But it's here that we get the gold from the Neogene. Okay, so if we're going to apply dynamic fertility to targeting, we do need some new terminology. So I like to think of fertile geodynamic scenarios. So these are the situations where the Laux or fume process can operate. So these are anomalous states relative to the background evolution of the origin. And when they occur, mineralization will form. And I may not have the time to go into it in this talk, but we do have to think of these things at nested scales. So we may have a local fertile geodynamic scenario nested within a broader favorable context. An example is the Arica Bend, or the Bolivian orocline provides anomalous deformation in the Neogene, but that's within the overall context of that margin being more compressional in the Neogene. And then the FGA, or a fertile geodynamic anomaly, that's just a spatial extent that we can map these things out at. And in this framework, that becomes the ultimate output of any regional metallogenic analysis. And I don't want to spend too much time on this because these thoughts are really quite immature at this point, but we can identify various types of regional scale fertile geodynamic scenarios. And we can think of them in terms of, are they going to work for the Laux process, or are they going to work for the fume process? And the two that I'm kind of most interested in is a type 1 compressional anomaly and type 2 transition to extension. And a simple model, but it's a model that actually does work in real life examples, is if we think of the evolution of a convergent margin over time, and we think of the parameter that we're going to pay attention to is a slab dip angle, which is a function or is a strong proxy for the degree of compression versus extension. And we think of a cycle that we often see, and this is the Laramide, but many other examples, is as we go more and more compressional and the slab angle gets flatter and flatter, and this compressional anomaly builds up, we've got a type 1 fertile geodynamic scenario. And that's where we'll drive the Laux process, but we also can drive the fume process, because we're activating, particularly if we're activating strike slip faults at a high angle to compression, which is why we have that correlation. But then we'll go amagmatic and not much will happen. But this is sort of basically a pretty unstable situation, because convergent margins want to spend most of their time rolling back. So then we'll switch back to extension. And it's right at that point that we'll actually have a type 2 fertile geodynamic scenario. So this is basically Carlin, sort of Bingham Canyon, etc. So here's an example from Northern Colombia. It's sort of a little bit of a messy slide because it's actually got my architectural working out on it. But the point I sort of want to make is that, let's probably move this screen. So these are a series of time slices, and these guys didn't think about mineralization at all. But what they were trying to do is infer the geometry of the subduction zone in this sort of relatively young context. So and the little triangles are the arcs, and most volcanoes are forming above about the 100 to 120 kilometer contour, depth contour to the top of the Benioff zone. That's pretty typical. So it's basically the brown-green transition here. And you can see between 14 and 9, we've got a subduction zone. It's forming. We're not forming any mineralization. But then we start to see the slab flattening, and we start to see magmatism declining, and then it becomes totally flat and we don't see any magmatism. So what's interesting, and I'll highlight this in a minute, but it's mineral. This is the time where the slab starts to become flat. So this is what I would call a type 1 geodynamic anomaly. And then we shut the system down. So just to summarize, if I'll put that up there. So if I just take their geodynamic interpretation, this period sort of 9 to 5.9, remember they weren't looking at ore deposits at all, but then I just plot on the significant ore deposits that occur at this age, and I plot on their dates. You can see it's sort of a very good correlation between those ore deposits and this sort of more or less sort of amagmatic period of flat slab. But then after 5.9, magmatism shuts down, the slab goes totally flat. Don't worry about this because it hasn't formed yet. And we don't have any ore deposits. But then from 4, what happens is we have a slab tear, and magmatism starts up again south of that tear. But the key point is we get mineralization happening again. So these are the Vetus California veins, these really young Pliocene veins, still above what we would expect to be the Paleoarc position, but associated with this transition to extension. So I think this is really quite a nice sort of Pliocene type example of the relationship between geodynamics and these punctuated periods of ore formation. We can say a few other things. So within the context of a type 1 fertile geodynamic scenario, we have a pretty clear relationship between the strength of our porphyry copper endowment and the intensity of a compressional anomaly. And this is quite an old Sillitoe and Perello summary from small porphyries in relatively only slightly thickened crusts through to giant porphyries in the really thick crust. And you can actually see that as a comparison of various pulses in a 100 million year history of the Andes, or you can actually see that progression of gradual thickening and buildup of mineralization potential within one single event, such as the 45 to 30 MA incaic orogeny, with the biggest deposits happening last. So if we put that together into a conceptual model, and this is sort of loosely based on the Peruvian margin, and for what happens during a type 1 fertile geodynamic scenario, the idea is that the copper fertility is really associated with the geodynamic anomaly in the arc. And what we see, particularly when you look at places like Peru, is that porphyry copper deposits don't particularly care about pre-existing architecture. They're really a function of the geodynamic anomaly at the time they form, whereas gold is actually very, very different. And the gold deposits are occurring generally in domains or corridors, and I think they're largely controlled by these domains of old translithospheric faults that have had multiple ages of pre-existing mineralization. So in Peru, that might be from the sort of Paleozoic through to the Miocene. So the sort of mnemonic that I like to say to talk about this is that gold fertility has a memory, but copper fertility does not. One of the other things that this model predicts is that extensive syn mineral lower crustal melting is going to be a pretty negative factor, particularly for the fume process, but probably also the Laux process. But in the Laux process, the scenario that forms these things results in reduced volumes of magma anyway coming up, so maybe it's less of an issue. But if we look at now the Superior, one of the really interesting things about the Superior is the sort of heterogeneity and endowment between the greenstone belts and these coeval, what they call sort of metasedimentary belts. And these metasedimentary belts are basically the same age of rocks as these Temiskaming late basin sediments. It's just they're the deeper water equivalent. So the sort of rifting event, if you like, and we see the same thing in the Yilgarn, it's just not as clear, but the same sort of rifting event that produces the late basins, and I've kind of exaggerated them graphically here, but yeah, these Temiskaming trends, you can almost see these things as rivers flowing into, in this case, the sort of Quetico rift basin. And the interesting thing we see is that while the structures along the margins of these basins are often quite well endowed, we have very little endowment within these basins, even though they're being deformed basically exactly coeval with the gold event. But what we are seeing is high temperature metamorphism, granulite facies metamorphism. We're seeing crustal melting. So what we're probably seeing is a hot rift where we just don't have that connection from the mantle. At the edges, yes, and around it, yes, but not in that actual time. And what's interesting about that is if we fast forward 1 billion years of geological history to the sort of the reindeer zone, which is really just Paleoproterozoic sort of reworked superior margin in Manitoba and Saskatchewan, we see the same thing. We see these earlier greenstones, and then we see a superimposed rift full of peelite, which is basically a late basin, and it gets metamorphosed and anatexized and all of that, and it has got no gold in it either. So I think this is pretty interesting. I probably also feel that this relationship between the need, or this idea that we don't want soggy, really hot, weak, lower crust, probably explains why in Archean granite greenstone terrains, which can have multiple cycles of volcanism, we typically only see gold mineralization right at the terminal cycle and after we've had a big granite bloom, because I basically think what happens is the big granite bloom moves the high heat producing elements to higher in the crust and therefore strengthens the rheology of the crustal profile so that we actually can have this connection for these low volume melts through to the surface. We often have multiple phases of pre-existing volcanic mineralization, things like VMS and nickel, but only one phase right at the end of gold mineralization. So I think that sort of brought me to the end of the talk. But just to summarize, I think recent advances in our understanding of convergent margin metallurgy do allow us to propose an integrated regional scale unified hypothesis. And in principle, this provides a powerful predictive framework to support regional targeting. A key learning is that regional scale geodynamics, and in particular, how that varies in space and time at the 1 to 10 million year timescale, is a critical thing to understand. So if we want to understand better our ore-bearing environments, we've got to understand better these variations in geodynamics. And obviously, many of the examples I showed you are Pliocene or at least Cenozoic. So we see the patterns are clearer. Obviously, that's going to be harder as we look back in time, but we've got to think about what are the proxies that we're going to look for in terms of these older events.